session of Mathematical Physics Seminar, and today we have the pleasure to welcome Sylvie Corteel. Sylvie Corteel is a CNRS in IRIF, Computer Science and Combinatorics Lab, and she has been for a few years in Berkeley. And she will talk about domino tilings of the generalized Aztec triangle.
Okay, so thank you, Jeremy. Thank you for the invitation. I guess I'm a combinatorialist, so I'm going to count. Maybe that's not what all you do every day, so bear with me with that. And this is joint work with my student at Berkeley, Freddy Huang, and Christian Kraften-Taller. So as I told Jeremy, I'm a bit frustrated because I wanted to give this talk and put the paper on the archive before, but I failed the fact that I put the paper on the archive before giving the talk. But hopefully that's going to push me to finish the paper. I'm going to talk about domino tilings, and even though I guess maybe all of you know a lot about counting domino tilings, I'm going to decide to go slowly, okay, and try to see what kind of techniques I like to count this type of tilings. So first, what's my question? Okay, so I'm going to choose a subset of Z squared. That's my domain D. Okay, so here is an example where the domain is just 6 by 6 square. And what's a tiling is I'm going to cover my domain with dominos. Okay, so dominos are just 2 by 1 or 1 by 2 rectangles. Okay. So let's do an example. Okay. So as you can see here, I cover my whole domain by 2 by 1 or 1 by 2 rectangles. And so that means that my region is tileable. And of course, when you take something as simple as a square, you always know that if one of the sides is even, this region is always going to be tileable. But I don't want to answer the question, is it tileable or not? I'm an enumerative combinatorialist, so my question in general is how many tilings of a given domain? So I choose a domain where I know it's always tileable, and I'd like to answer how many tilings of a domain can I have. So that's going to be the theme of the talk today, okay, is when you have a region that behaves fairly well, are you able to count the tilings of this region? And so for the square and for the rectangle in general, okay, this question has been answered more than 60 years ago. And I give the case where the rectangle, both sides are even, okay, but if only one of the sides is even, you also have the same type of formulas, okay. And so here is the result of Castellan, Temperley, and Fisher, is that the number of domino tilings of a 2m by 2n rectangles is this formula, so 4 to the m times n, and then you have these two products, j from 1 to m, and k from 1 to n, of the sum of the square of cosinus, so cos squared j pi over 2m plus 1 plus cos squared k pi over 2n plus 1. Okay? So in combinatorics, that's what we would call a beautiful formula, a nice formula, because it's a nice product, okay? And even though this was not proven using combinatorial techniques in the 60s, then 40 years later, so Volker Strel gave a more combinatorial proof of this, and he calls the paper Counting Domino Tilings of Rectangles via Resultant. But what you're going to do is first you're going to start by a tiling, and first you're going to biject it to some other combinatorial object, and through a bunch of bijection at the end, you can understand why you have this nice product formula.
Okay. You mean it's a purely bijective proof?
No. So it's changed the proof to a few things that are bijective, and at the end he computes a resultant, but that's fairly easy to compute.
What is the result?
So I don't exactly know, but it's something you compute on matrices. But the first step that he does, and that's what we're going to do today too, and now it's fairly classical, is first you look at your domain, okay, and first you look at it as a checkerboard, okay. So you're going to choose to one of your favorite square here, so for example this one, you're going to choose to color it white, and then each time these 4 neighbors you color it gray, and like that you get your domain as a checkerboard domain. And what you see there is finally you don't have only 2 types of dominos, but you have 4 types of dominos. Now I started with a priori like 2 types of dominos, my horizontal and my vertical ones. But now that I color my domain as a checkerboard, I'm going to have 4 types of dominos. For the horizontal, the ones where the gray is on the left, and the ones where the gray is on the right, and the same for the vertical ones. And so why is it nice to see that as not 2 types but 4 types? Is that now I can make a bijection between my 4 types of dominos here and certain steps. Okay. So I have my 4 types of dominos, and now I biject them. So I decide that now if I see white at the bottom and gray at the top, I put an up step. Okay, here I'm going to put a down step. For this one, I'm going to put an east step. And for this one, I'm going to put nothing. And when I do that, okay, I get a bijection between my domino tilings, okay, and now a system of paths that are going to be non-intersecting, because you see the way I chose them, the paths are never going to share a vertex, so the paths are non-intersecting. And also you can see that the beginning and the end of my paths are always fixed. Okay, so in that example, I'm going to have always a path that starts here, here, and here. And the paths are going to end on the right, here, here, and here. Okay, so I biject my problems of counting domino tilings to now counting some systems of paths, okay? And you all probably know that if I want to count non-intersecting paths, now I can write that as a determinant. Okay? So that's the Lindstrom-Gesell-Bieno lemma. Okay, whenever you have a system of non-intersecting paths where the starting points and the ending points are fixed, you can write that as a determinant. And what do you have in your matrix is now if I call my starting points U1, U2, U3, my ending points V1, V2, and V3. Okay, what I put in my matrix Mij, will be the number of paths from UI to Vj. Okay? And if I can compute this determinant, then I can count my number of tilings. Okay. And so these paths are not too complicated, okay? You can see that there are paths that have 3 types of steps. I can go down, I can go up, and I can go east. And then they're going to have some conditions that are going to come from the boundary on the top and the boundary on the left. Okay. But that doesn't mean that this determinant is easy to compute in general. In general, that can be hard to compute. Okay? So what Forkenstedt does is when he starts from his path system, now he changes it to some kind of heaps. Okay? That were a theory developed by Bieno. And thanks to heaps, he can also do another combinatorial step towards computing this formula for domino tiling of the rectangle. Okay.
So if you just wanted to keep track of those paths, slice the system and go from left to right, then your your description is not completely local, right? Because the horizontal tile on the bottom, it must take 2 consecutive steps that go straight. So you could not simply write some evolution operator that would take you from one row to the next without memorizing also that you have taken the first horizontal step out of 2.
Yes, it's true. So, but also for the vertical step, they both use 2 squares on my steps. So, but still, yeah. So I can't really slice it column by column.
Yes.
But still, if you know, for example, like the height of the path, because of parity conditions, you kind of know how many horizontal steps you did. But I don't know if that helps to write a column.
Parity, yeah, I see, right, because you change the other 2 steps, they change the parity of the vertical position.
So for example, here, I went up by 1, so I know that the number of E steps plus the number of, the number of up steps minus number of down steps is equal to average.
So if you're on the wrong parity, you know that you made your first horizontal step and then you should make the second.
Yes. But I rarely write transfer matrices, so maybe I'm going to say something that doesn't make sense. And so that's the theorem in general, okay, is if your domain behaves fairly well, you can fix your starting point and ending points, then the number of tiling is going to be computing now this determinant, and the size of the matrix is exactly the number of steps here, okay, the number of points of the starting point. So another classical domain that enumerative combinatorialists have been interested in is also probably something you all know fairly well, is the Aztec diamond. Okay, so that appeared a bit later, at the beginning of the 90s, in relation to alternating sign matrices, okay, because the tilings of the Aztec diamonds are in bijection with alternating sign matrices where you put a weight 2 on each minus 1 in the alternating sign matrix, okay. And so this is a region, okay, of diamond shape. So it's a sequence of shapes here, and the size of the diamond is the number of corners on the waist, okay. So I draw a few diamonds. So for n equals 1, it's just a 2 by 2 square. For n equals 2, it's that little cross, okay. And n equals 3, n equals 4, and you can continue like that. Okay, so the shape is easy to draw, is that you go 2 up steps, then n corners, then 2 steps, n corners, and stuff like that. And then you can ask the same question we've asked on a rectangle, is how many tilings can you do? Okay, and it's a result of Elkies, Cooper-Bear, Larson, and Propp. That it's a power of 2. Okay? So if the Aztec diamond has size n, okay, then the number of domino tilings is 2 to the n plus 1 truth. So the numbers grow very fast, okay, so I can only draw them up to n equals to 2. And you can see that if n is equal to 2, you have these n tilings of the Aztec diamond. And it's easy to produce them because you can start with, for example, the tiling with all horizontal tiles. And then each time you can pick a little square that would have 2 horizontal or 2 vertical dominoes. You can do a flip, and this way you can produce all your tilings of the Aztec. So by now there's many proofs of why this is such a beautiful formula, why you get a power of 2. And one of them that's very nice is called the domino shuffling. So the idea behind the domino shuffling is that you start with a tiling of size n-1, okay, that you already randomly produce uniformly. And what you're going to do is you're going to push your dominoes towards the outside. and you're going to cancel some of them, and you're going to make your Aztec diamond grow, okay? And you make it in a way such that at the end you have some holes, and you hope to have exactly n holes, okay? And then you flip n times a coin, that would give you the 2 to the n. And then you show that the number of Aztec diamond of size n is 2 to the n times the number of tiling of the Aztec diamond of size n minus 1. Okay? So that's a proof that's very cool for many reasons. First, it gives you a very simple explanation of this enumeration formula, but it also gives you an algorithm to produce a random Aztec diamond. Okay, so and then when this was done, people could like make simulations of very big tilings of the Aztec diamonds. They saw that actually a random, so I thought I put a picture, but I thought I forgot at the end. Okay, if you produce a really big tiling, okay, it's going to be pretty amazing. The 4 corners are going to be frozen. In the middle, it's going to be mixed. And what you have is you have an Arctic circle that separates the frozen part from the liquid part. So all these things have been proven rigorously now. But today I'm just thinking about compound. So how can you count the domino tilings of the Aztec diamond? So I'm going to see another way to biject from my domino tilings to another type of combinatorial object. Okay, and the way I'm going to do that is I'm going to look at my 4 dominoes, and in each domino I'm going to put some information.
So you don't want to use those paths?
I could use the path. Yeah, I can prove it with paths too, but I chose not to do it there. So the paths start here and end there, and they go like that. And so, for example, you can prove that the top path is going to go like a semicircle, and you can use path also to prove the Arctic circle. Actually, it's very cool to prove it with paths to get that you get the 2 to the n.
Like a disaster for a transfer matrix. Somehow you would have to scan it a strange way.
So I could do it with path, but I'm not doing it here. I'm going to do it with white and blue dots. Okay. And so what I'm doing there is I look at my 4 types of dominoes again. And then I make this choice that if I have a gray particle on the left or on the top, I'm going to put 2 white dots. I guess. And for the other 2, I'm going to put 2 particles. Okay. And the claim is then I can take off the tiling. If I just know the white and blue dots, I can go back and find my tiling. Okay. So the same way that before I could just look at the path, now I can just look at these white and blue sequences. Okay. And then I can get. So a priori, what do I get from that? Okay. And so what I do. So that's my 4 types of dominoes. Okay, so I choose that if the dominoes start in white, okay, I have particles, and otherwise I have holes. But now I'm going to slice my Aztec diamond not by column or by rows, but by diagonals. Okay, and I'm going to read so from bottom to top, I think, but I could do also top to bottom. Okay, now I'm going to read each diagonal, and from each diagonal, I'm going to get some combinatorial interpretation. And so what is this interpretation? Is I'm going to see that each diagonal now coming from my tiling as a Maya diagram of a partition. So whenever you have an integer partition, so a sequence of non-increasing integer. You can write it here as 6, 3, 3, 1. You get its Ferraz diagram, but you can also see that as an infinite word in black and white. Okay, so a word that would start with an infinite number of blacks, and then I follow the border of my diagram, okay, where I would see white when I go east and black when I go up. Okay, so I have this infinite word here, but I have a unique way to center it. Okay, there's a unique center, and it comes exactly from the Durfee square of the partition. So there's a unique way in my infinite sequence here to see a point where the number of blacks to the right is equal to the number of white to the left. Okay. So you have to see that as like a word that's infinite with only black on the left, only white on the right, and then a finite region that can be disordered and has a unique center. Okay. And so, a priori, what's the link between that and these domino tilings? Because now each of my diagonal, okay, is finite. Okay, but the way to make it as an infinite word is you can see it as now to the left. I don't know what, or maybe I have to do that. So I can put an infinite number of blacks on this diagonal and an infinite number of white on the diagonal, and then I make it as a word as a partition. Okay? So now I see this finite domain tiling as kind of embedded in an infinite domain, okay, where what I have to the left and to the right are completely frozen, only black and white particles. And so let's do that on this example. Okay, you have to believe me that if I read now the sequences of partition coming from my Aztec diamond, okay, I will get here the empty partition, here the partition 2, because this black particle has 2 holes to its left. Now the partition 1, the partition 2, 1. Oh, I forgot to write this one. This is the partition 1, 1, 1, 1, and the empty partition. Okay, so now I translated my problems of counting domino tilings to a problems of counting some sequences of partitions. Okay, but of course I cannot find any sequence of partitions. Okay, the way I can go from this partition to the next one, okay, is non-trivial. And so that's what we did with Jérémy and Guillaume Chapuis, is that we showed that there's a bijection, okay, between the tilings of the Aztec diamond on size n and some sequences of partition. Okay, so I have 2 n partitions here. The first one and the last ones are the empty partition. And then to go from one to the next, I have very specific rules. Okay, so if I go from a partition that has an odd index to a partition that has an even index, what I do is I add what we call a vertical strip. Okay, so I had some piece of Ferraz diagram that has at most 1 cell in each row. And when I go from a partition that has an even index to a partition that has an odd index, what I do is I take off a horizontal strip. So I take off a piece of the Ferraz diagram that has at most 1 cell in each column. And so why are you happy? Why this is making it easier now? Okay. A priori, why this helps to count the number of tilings. Okay. And so the thing is, okay, what's behind that? So
but the number of transition rules is growing a lot with the system size, no? I mean, if you take a sufficiently large Aztec diamond, then you can go from a given partition to many other partitions.
Yes, but as you have to come back to the empty partition, you cannot go too wide.
Yeah, sure. So can you make the rules more local by adding a little bit of the line at a time? So instead of going from one diagonal line to the next diagonal line, suppose you go from a diagonal line to a diagonal line with some kink or something, so that you just go past one square of your lattice. Will you get something simpler?
I'm not sure I understand the question. So.
Well, when you do transfer matrices, you don't need to transfer a whole row at a time. You could transfer just a little bit, like going from a line to a line that has moved forward by some kink.
Okay. Yeah, so here we go full diagonal, but I guess what the dominos tell you locally how things move, no?
Yeah.
But still we go one full line to one full line.
If you see this as a configuration of particles and foams, then the partial thing is like one particle moves and then the second particle moves. So
Yeah, something like that. Something like this.
So you'd like to see that as like a bunch of steps rather than seeing.
Yeah, so you have somehow a line with certain particles, and then you start updating. You say this guy can do something, and then the next guy can do something, and so on, and then you sweep through the row like this.
Okay.
Just wondering if that's.
I think you're going to present the connection with vertex model, so it's a bit like in the vertex model you can make a transfer matrix where you had a full row of squares, and maybe you could add one square at a time by doing what you suggest. Maybe I think it's the same. Maybe.
Yes, so let me tell you why this helps to count the number of tilings, okay? Is that you can see actually the sequences of partitions as also 5 vertex models, okay? So what I'm telling you is that if I want to take off a horizontal strip, then I can see that as a 5 vertex model where I don't have in the 6 vertex model the cross, okay? And if I take up by duality a vertical strip, then the vertex I can't have is this one, okay? So you can translate these things of sequences of partition as computing the partition function of 5 vertex models. Okay, so namely what it is it for the okay, so I lost the slide I wanted, but what I want to compute is this type of partition function. Okay, so I start here with the empty partition. I'm going to end the empty partition, and I'm going to see my sequences of partition as certain 5 vertex model. Okay, and so why now things are easy to do is that if I start with this model, okay, where I start with the empty partition, I take off a bunch of maybe vertical strip, I add a bunch of horizontal strip, and I end up at the empty, then I have just one unique way of doing that. Okay, so the partition function of this model here is just a monomial. Okay, now what I can do is what I have behind this 5 vertex model is I have the Young-Baxter equation that I can use. Okay, and because I have the Young-Baxter equation, I can put a little cross here and make it travel to the right. Okay, and the Young-Baxter equation tells me that the partition function of my model on the left is equal to the partition function of my model on the right. Okay, and if you check, I guess I didn't write you the weights of things coming from the Young-Baxter equation, but the cross on the left is going to have weight 1, and the cross on the right is going to have a certain weight, that's the inverse of 1 plus x1 times yn. Okay. And so I can continue like that, and what I can show is, so I told you that the partition function of this was just a monomial, and the partition function of this by the Young-Baxter equation is just equal to this one times exactly the inverse of partition.
This has to do with a specific boundary condition that you choose.
Yes, I chose, so the bottom is empty, the top is empty, and the left and the right are chosen so that things are open. Okay. And so I get something way more information than I had before, is that I can follow the weight of each partition on my layers. And of course, if I put xi and yi to be equal to 1, I get back that the number of tilings is 2 to the n plus 1 choose 2. Okay? So the idea behind this is that if you use these like 5-vertex model, or what we call also in collaboration with Sanjay rare yard graphs, you can compute these number of tilings, but you can also get some more information, and that can help after to compute some asymptotics on your tile.
I lost track. Which boundary condition is now the Aztec diamond?
So the Aztec diamond is like the bottom and the top are empty partitions. It's all white on the right, and it's white when it's purple and black when it's gray.
And the other one on the top?
This one?
Yes.
So it's exactly the same. You see the gray have black on the right, and the purple have white on the right. So the rows travel with their border condition.
And that's easier to compute.
So this one is trivial to compute because there's just one configuration.
Okay,
all the paths are going to the right. This one is completely frozen on the right.
Okay. So if I take away all the spectral parameters and stuff, then I have 1 equals to 2 to the n divided by 2 to the n.
Yes. Yes, so this is 1. I guess I changed to m here. It's 2 to the n plus 1 choose 2 divided by 2 to the n plus 1. Okay, so I'm pretty slow. So maybe you won't get the end of the story. But anyway. So let me go to what I want to talk about today. Okay. So I guess it's something that's defined by your colleague Philippe Di Francesco. It's what he called the Aztec triangle. Okay. So why this is a triangle, I don't know. But anyway, so we're gonna look at a shape that's like Aztec style on the top. I have n corners, okay, then like that. Then I have n minus 1 corners, so here I took n equals 3. And then I go down 3, and here I go down 2n. And then what I have on the southeast, okay, is a double staircase. Yeah, I know why I didn't do a blackboard talk today. So, okay, so small staircase here, straight line, and double staircase. Okay? So that's what Philippe Di Francesco called the Aztec triangle. Okay. So why did he study that? Okay, is that he showed that the number of tiling of this Aztec triangle, okay, is equal to the number of 20 vertex configuration of this, I don't know what's the name of this shape, but what you have is you have a square, okay, here, and then a triangle under the square, okay, and then you have some fixed boundary conditions that seem to be, so on the top, everything exits. On the right, everything enters, and then here there's some, everything exits, and here everything enters. So it's a bit like the 6-vertex model. So you fix your boundary condition, but here you don't have a square, you have this kind of square with a triangle put on. And so how do you prove the kind of thing? Is that you show that this is equal to a determinant, that this is equal to a determinant. And then you prove that the two determinants are equal. So it's not what we I guess. In combinatorics, we like bijective proofs, but this is not a bijective proof. Okay? And so what's this vertex model? So this was studied by Di Francesco and Gitter, and then by Di Francesco. It's just like the 6 vertex model where you look on the square grid. Here you are on the triangular grid, okay? And at each vertex, you want to have to make sure that you have 3 incoming edges and 3 outgoing edges. So the partition function of this model is also a counting problem. In how many ways can you choose 20 vertex models here to make sure that all the configurations are okay? So locally, each vertex has 3 incoming edges and 3 outgoing edges. And so the conjecture of Di Francesco is that this number of tilings, okay, is a nice product formula, okay, something we call very nice, is that it's a power of 2, 2 to the n choose 2, and then times a product of ratio of factorial number, okay, namely from j equals 0 to n minus 1, or 4j plus 2 factorial divided by n plus 2j plus 1 factorial. So what Philippe could do is that he could write this partition function as a determinant, and that's really kind of easy to do, is really using just this path idea, okay? And I guess I call him Di Francesca, yeah, I'm sorry. He said in Oberwolf 2022 that this was proven by Kuchan, but I didn't see the proof on the archive. So using
what does the bracket UIVG?
So it's the coefficient of u to the I, v to the j of this. Yeah. Also, maybe you don't write it like that. Yes. So I look at this rational function as a generating function, and I take the coefficient of u to the I, v to the j. So let's look at that, okay? Let's look at that as a tiling, okay? And if you do this thing, so I'm just going to rewrite is u to the I, v to the j, okay? So this partition function, Zn, is a determinant of what we call in combinatorics the Delanois numbers, okay? So these are paths that go up, east, and down. Okay, and that have 3 kinds of steps and start at 0, 0, and end at yj. And so we have some pretty nice enumeration formula, namely the sum on L, I choose Lj to the L to the N. Okay, so it means you basically do I east steps and j north steps, and then L is the number of like that things are horizontal here. Okay, you choose some corners that are going to be horizontal. But a priori, this is not the kind of formula where it's easy to compute a determinant. Often when we have easy formula for determinants, we like the numbers in the matrix to be already products, already binomial. But here we have a sum, and so this is hard to compute the determinant.
Sorry, I have a basic question, but why are we interested in these special shapes? Is it like for an arbitrary shape you couldn't do the counting, but for some very special shapes you can?
Yeah, so in general the counting is a hard problem. Probably you can prove that it's sharply hard. So, and I guess you're interested in finding some shapes where we're going to have like, yeah, first of all beautiful formula, and also what's behind is often some like also integrability or symmetric functions, some things like that. The shapes that are going to have a nice behavior. If you're not convinced, but you'll have to bear with me until the end.
But the integrability part, the one that was so nice before, with these purple lines moving down, could this apply here?
So you're going to see. I'm not done, I guess. Okay, so we're going to do the same thing. Okay, so we're going to slice this generalized triangle. Okay, and we're going to do exactly what we've done for the Aztec triangle. Okay, so here I read my partitions from top to bottom. Okay, so in my example, I have the empty partition, then the partition that's just 1, okay, the partition that's 2, and then the partition that's 3, 2, 3, 2, and 3, 2, 1. Okay. And so if you look at this, okay, what you see is there's a bijection between tilings of the Aztec triangle of size n, and now I have these sequences of partition, okay, that are a bit like what I had with my Aztec diamond, except now I always increase. Okay, so in the Aztec diamond I was going up, down, up, down, up, down, starting at empty, ending at empty. Here I go up. Okay, I start at the empty partition. Okay, I end at the partition that's what we call the staircase partition, n and minus 1, 2, 1. But I have now this more difficult condition, okay, that at step I, okay, the number of parts of my partition is bounded, okay. So namely, lambda I has at most the ceiling of I over 2 parts. Okay.
This is something which is not implied by the other conditions. It's not just implied by the other properties, you have to add this extra condition.
Yes, so it's really the fact that you're going straight there that adds this condition of the parts. So it's coming from the shape of the
If you take another shape, if you remove that condition, do you get another shape that you find?
Yes. So you would go like, I think it's part of the radial graph or steep tiling, like you would get some like staircase on the left. I don't remember exactly what it is. But, and so if I don't have this condition, actually, then I'm in the world of supersymmetric functions. Okay, what's behind that is a super short function. But now I have this extra condition that makes things more difficult. Okay? And so now let's look at the generalized Aztec triangle. Okay? The first condition you can say is, why do I have to always end at the staircase shape? I could end at any partition with size n. Okay? And then look at these sequences where I add a vertical strip, add a horizontal strip, vertical strip, horizontal strip. And then I put the condition, I still have like what's called often the symplectic conditions about the number of parts of my part. And then I don't always have to have exactly an even number of partitions. I could choose in general to have now a sequence, okay, of maybe odd or even number of partitions. Okay, so that's what I want to look at, these generalized Aztec diamonds, where I look at these sequences, okay, where I end into any partition with n parts, and then my sequence can have 2n or 2n plus 1 partitions. And so that's what I want to look at. So I have a sequence of L partition that start at empty and at a partition mu that I fixed. And then between an odd and an even and odd partition, I add a horizontal strip. And between an odd and an even partition, I add a vertical strip. Okay. And then I force my partitions to have a bounded number of parts. Okay. And so you can draw this thing when L is even. Okay. You can just slightly generalize this idea where the west, the south, the northwest, and the northeast conditions are the same. But what you have here is when mu is fixed, you decide the southeast boundary with the Maya diagram of the partition mu. Okay. And then you can see that the number of tilings of this general case, okay, is a determinant of these Delannoy numbers, where, of course, if mu is just a staircase, you get back the regular Aztec triangle. But if L is odd, okay, so here you can see, because of my gray-white thing, okay, when I look at the Maya diagram of my partition mu, I chose to add in my domain the white particles and not the purple particles. And when L is odd, actually I do the opposite, okay, in the Maya diagram, I add in a domain the black particles that I drop like here and not put the white, okay. So I have a way to make this generalized Aztec diamond shape. And now for this case where L is odd, the number of tilings is just now, I guess I wrote H here, but where the H are a sum of two Delannoy numbers. And so that's the theorem that we can prove, is that if mu, okay, is of the staircase style, okay, so I have a k minus 1 up to 2 to 1, I have a bunch of zeros after, then the number of tilings of this generalized Aztec diamond is always a product formula. Okay. So this looks a bit different from the Di Francesco formula, okay, but you can find back the Di Francesco formula. I didn't write it. But if k is equal to n and L is equal to 2n, okay, you can rewrite this. I guess when you have products, you can rewrite them differently, and you get back the conjecture of Philippe Di Francesco.
So in this Delannoy number, they were difficult to compute the determinant, but you found a way to.
Yes, so how do you do that? Okay, so now you use really the fact that now you have something that's polynomial in L. It's not just a number you're looking for, but you have a polynomial in L here, because it depends on K and on L. And so what you're going to do is you're going to look at the case L even first. So this, when we have a determinant with Delannoy number, so you check that what you're looking for is a polynomial in n of degree k plus 1 choose 2. You compute the coefficient of the leading term of your polynomial, okay? And then you do some very difficult step that only Kratenthaler can do, okay? And what you're going to do is you're going to get your factors out one by one by using some hypergeometric manipulations, okay? And some of them can only be done with computer algebra. Okay, some part of the proof is done using the computer. Okay, but you can get this formula, okay, for every L and every K. So the idea behind is not easy, but the proof can become quite technical. So that's the case where L is even, but when L is odd, and you want to compute this determinant of H, which is a sum of two Delannoy numbers, actually, if you prove the L even, the L odd comes for free. Okay, you can do some simple manipulation of row and columns, and you can extend the result for L even to now you don't only compute it only for integers, but also half integers. Okay, and you prove that what you had proven here for D1, then the formula for D2 comes for free. Okay, so namely that D1 of K of n plus 1/2 is D2 of K of n. You have to work hard only once. Okay, you prove the L even case, and the odd case is just very simple from the even case. Okay. And so what comes out of that, we hadn't seen it from the formula, okay, is that there's a bijection between tilings that are coming from the Aztec triangle. Okay, so if I look at case 1, so a sequence of 2n partitions, where the mu is n minus 1 up to 1, so the mu is a staircase, And if I look at case 2, so sequence of 2n plus 1 partition, where I force my final partition to be n minus 1, n minus 2, 1, 0, there's a bijection between these two families of tilings. Okay? And these are the family that came from the 20 vertex model. Okay? So if n equals 1, the bijection is easy. My two shapes are exactly the same, and I have one tiling. I shouldn't have put an S. So if n equals 2, okay, the two shapes are like that, and it's very easy to see because you're forced to tile the bottom here, and then the two shapes are the reverse of each other. Okay. But if n equals to 3, okay, then it becomes non-trivial, and n is equal to 4. You see that the shapes, they look fairly similar, but the top part is different. Okay, here I go up n steps and go down n minus 1 steps. And here I go up n minus 1 steps and go down n steps. Okay, and the two formulas, they look quite different, but you can prove easily that this like big product here is equal to this product for any n. Okay. And so that's a nice combinatorial question to give a bijection between these two families of tilings. And so now, what's the vertex models that come from this? Is actually you can still translate what I told you as a vertex model, but unfortunately, the shape you get from the vertex model is the staircase shape, okay, and then you don't have the Young-Baxter equation that you can work behind, okay? So now, the border here is a staircase, and so there's not nice proofs coming from vertex model. And you can also do a bijection between these sequences of partitions and a certain of tableau, okay? So I wrote funny tableau because I don't know which name to give them. So they are tableaus that are a mix of super tableau and symplectic tableau, okay? And they are in bijection with those tilings. So the question is there some kind of a super symplectic functions that's behind that? And also, why is it only in the staircase shape that we have product formula? Or could we give some formulas for other shapes that wouldn't be product, but maybe sum of products? And okay, so that's my conditions on my tableau. Okay, they're both super semi-standard tableau, but with this extra symplectic case that comes from the number of parts in my sequences of partitions. Okay. So merci for your attention.
Further questions?
So instead of counting the number of tilings of certain shapes, I mean, is it possible to enumerate all the shapes that have a given number of tilings, like shapes with 3 tilings, for example?
With 3, I can probably do it. But I don't know if anybody asked itself the question, if you give yourself a sequence, what would be all the shapes that would give you? That seems like a quite difficult question. No? Maybe not for a physicist, I don't know.
In the last case, you cannot do this simple thing of having a certain diagram which would be trivial to compute and then use Young-Baxter to evaluate.
So I don't.
Because you still have blue, red, white, but you cannot put all the reds to the top or the white to the bottom.
So I don't think so because I don't have any more symmetric functions. So usually, and also before when I'm moving rows, they were all having like kind of the same length. So I don't know how I would rearrange them. But
the difficulty has to do with a specific type of boundary condition you have to impose on the vertex model.
So, but the difficulty has to do with maybe it's the fact that I don't have rows of the same length anymore. So that's coming from this condition number of parts. So,
You cannot complete this row by something which is completely frozen. In the case before, it was probably possible.
so maybe I could. I would have to think about that. Yeah.
Why is the condition with the I/2 the flow was symplectic?
Okay, so usually symplectic tableau, they are the same tableau except the bar and non-barred entries form horizontal strips. So you look at sequences of partitions where you add only horizontal strips. So at even times you call it I bar and at odd times I, for example. And then the tableaux are called symplectic if in row I you see only entries greater or equal to I. So that's why I say symplectic.
Is there any relation to symplectic geometry?
So there's relation to what's called symplectic Shor function. Why is it symplectic geometry? I don't know.
Maybe it's related to the representation of the symplectic group.
Yes.
Is there any connection with Dan has worked on the symplectic Shor process?
Yeah, so the symplectic Shor process, you would only add the horizontal strips, but with that condition on the number of parts. So, but yeah, maybe I should look at what Dan did. That's a good suggestion.
I mean, usually these things, they can be Q-deformed, but maybe it's not so interesting, I guess.
So to find a Q analog of that. So I don't know, last week I saw a talk of Jessica Stryker, who said like her PhD thing was to find so you could take the number of alternating sign matrices, you could Qify all the factorials, and that was her work, supposedly work during her PhD to find the definition of the statistic on alternating sign matrices, and she said it's still open. Seems she tried for 15 years. So we could try here too.
Well, I mean, at least, I mean, I remember these two things, there are these Pierre rules, so you can replace Shor function by something.
Yes. But I think we tried to Qify and we were not getting a product formula, but we didn't try too hard.
More generally, is there any way of putting in interactions on those tiling models?
So actually that's
Or models?
so me what I study now, but not related to that, is I don't take one tiling, I take several tilings, and I define some interactions between each pair of tilings.
In physics, sometimes we put some energy if the things are parallel, or I don't know, some kind of. But I know it's not soluble. But it's interesting because they are phase transitions. And
There were some results, right? I mean, Toninelli and others, they looked at this. Toninelli and people.
So they put some energy between the paths or something like that?
Oh, it's very simple. So if you have two horizontal dimers or two vertical dimers, you give in each case you give.
Oh, so for example, here the power of 2. If you just want to count the number of vertical tiles, for example, give a power of q to each pair.
There's a way for a pair of two adjacent aligned tiles.
I think that would be corresponding to the alternating sign matrices where you put a weight per -1, and when you set the weight per -1 to 2, that's equivalent to the Aztec diamond, in that you interaction when you get away from this.
Is that solvable?
Probably depends on the boundary condition. I think it's available for some boundary condition.
But for example, if you want to put a queue to each vertical domino, so not just this is very easy to do.
Yeah, sure.
But and then because if it's a vertex model, you can compute lots of correlations and stuff like that. But like exactly counting two, yeah, I don't know if I will.
No questions? Thanks, Sylvie, again.